Better. Yeah, let me activate mine because then they might ask about you. I'll just say like put these people. Okay, guys. Now let's do two things. Yeah. Okay, guys, let's finish up. Let's finish up. So duodenum, and then, whoa, what is going on? So pancreas, oh my God. You're okay. So you're okay. You have no problem. All right. So duodenum and pancreas. Now we need to know some stuff about this. We're gonna ignore the endocrine pancreas. Okay, we're gonna ignore the endocrine pancreas. We will only talk about what? Exocrine pancreas. And those cells are known as what? Acinar cells. Very good. So let's say here is a bunch of acinar cells. And these acinar cells make glands. They make glands. And essentially they'll make a long tube. And this multiple tubes will connect to the single tube. Okay, so let's say here, here, and this will become pancreatic duct. Many of them. I'll just draw one or two just for simplicity, just to make it easier for us, okay? All right. Now the pancreatic duct will be joined by bile duct over here. Okay, bile duct. Bile duct. There you go. Doesn't Vader sound like that? Yeah, that movie, Star Wars. I heard people are waiting for this in a line. They didn't even sleep. They were so excited. That's a goal in life, I guess. One way to look at things. Having a goal of watching a movie. All your life you wait for that. Huh?
Waiting for somebody else to do the work.
Yeah, I mean, I don't know. I just get surprised sometimes with people like that. There's nothing else in life to do. To wait for a movie. Mazen's gonna tell me that you watch movies every day. What are you talking about? I don't intend to. They come to me. I don't go to them. Okay. Now, so we're gonna talk about this. Pancreatic enzyme would have to be secreted here. Now, I want to talk about, let's start with protein digestions first, okay? Protein. Let's start with protein digestion first. Protein digestion. Okay. Protein digestion starts in the stomach, right? We've discussed that part in the stomach. In the stomach, proteins are broken down into what? Peptides. Okay, peptides. So these peptides will come, and then when we reach this area, the duodenum, I'll put two P's. The peptides have to be broken down into dipeptides. Dipeptide. Okay? Now, how do we do that? Before we go to that, here we have cell known as I cells. Okay? And we have other group of cells known as S cells. Are we good so far? Okay. And of course, these cells will have brush border, right? Villi and microvilli. Okay, or the duodenum in general will have brush border. Okay, what activates the I cells, number one is fatty acid. Okay, number one is fatty acid. Fatty acid activates the I cells. So I'll put the thing that activates the I cells. Fatty acid is the most important one. Low pH, decreased pH is another one. Amino acids, another one. In essence, food particles. Glucose, monosaccharides, fatty acids, and amino acid in low pH, all of them will activate what? I cells. Are we good with that? Now, where is the low pH coming from? Gastric acid, right? The pH of duodenum should be around 7 or something. When it decreases, that means gastric acid is coming. At the end of the day, if you think about it, in its common sense, the cells of the duodenum should be activated by gastric content, food coming from stomach. Only then they should get activated, because the purpose of these cells is to digest that food coming from where? From stomach. So the only time they should get stimulated, they should get activated if there's need for them to do so. And when is the need? When food coming from stomach comes in contact with these cells. It informs them, hey, I'm here. Can you do something about me? Cut me into pieces, digest me, absorb me. Good. Now, eye cells will produce a hormone known as CCK, cholecystokinin. Cholecyst means chol comes from cholesterol, cyst from bladder, kinin means motility. Now, what cyst stores cholesterol? What cyst will store cholesterol? Gallbladder. So the term cholecyst is the name of gallbladder. Gallbladder has another name, cholecyst. Cholecyst. It stores bile, and bile is primarily made of cholesterol. Maybe I should tell you. I mean, it's okay. Let me tell you something. Bile. Bile is made of cholesterol, cholesterol esters. Write it down. Bile, the composition of bile. What is bile made of? What is bile made of? Okay. The composition of bile is, number one, cholesterol, cholesterol esters. That's two. Cholesterol esters. Bilirubin. That's three. Bile salts, 4. Bile acid, 5. Bile is made of 5 things so far, I think, right? Bile salt, bile acid, bilirubin, cholesterol esters, and cholesterols. And of course, there should be minerals and waters and other stuff as well, but just telling the major important stuff, okay? So as a result, anything that stores bile is based on cholesterol, because the majority composition is cholesterol, okay? So gallbladder, this green structure, gallbladder, is also known as cholecyst. Cholecyst. Now you can use the same term for urinary bladder, urinary cyst, urinary bladder, cholecyst, cholesterol bladder, same thing. Okay. So CCK is produced in response to amino acids, low pH. Now low pH of what? Blood? No, of the duodenum. Increased fatty acid content in the duodenum. All of these things will be in the duodenum. So let me just erase it here, because I wrote it here to create myself some space, or to make myself some space. Okay, so now the eye cells are activated by fatty acid. Number one, the most stronger activator of eye cell is what? Fatty acid, fatty acid. The strongest activator, stimulator of eye cell is fatty acid. Amino acid also activates them. Acidity, now acidity of what? Duodenum. Okay, so gastric acid or low pH, or in general food particles activates them. Good. So let's erase this again, because I need this space. When CCK is released, CCK acts on gallbladder. It causes contraction of the gallbladder. CCK causes contraction of the gallbladder. It squeezes the gallbladder. Now again, if you get confused, the first C stands for what? Chol or chole. And the second C? Cyst. Cysto in this case. And then the K for? Kinin. What does kinin mean? Or kinin? Motility. So this hormone increases gallbladder motility, which means gallbladder contraction. So if you contract gallbladder, whatever is within it, it will be squeezed out. It will be pushed out. Gallbladder contraction leads to increased bile secretion in the duodenum. Okay, look, bile is stored here, so we'll go here and it will be released here into the duodenum. Okay. All right, so that's one thing. Now CCK also acts on the acinar cells of pancreas. Again, it causes contraction of the pancreatic acinar cells or the pancreatic glands, exocrine glands, not endocrine. And what would happen? Pancreatic juice secretion is increased. So it causes secretion of pancreatic juice, especially enzymes. Especially enzymes. Okay, I'll give you the difference. Let's do something else now. S cells release secretin. 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 See, the S stands for S secretin. S cells produce secretin. Now, S cells are again stimulated by what? Amino acids, fatty acid, and pH. But the stronger stimulator of this is low pH. The stronger activator of CCK is what? Fatty acid. It makes sense too though. Guess what? Secretin acts on the pancreas. Secretin also acts on the pancreas to cause secretion of bicarbonate. Okay. Now, I'll tell you the difference. CCK and secretin both causes contraction of the gallbladder and pancreatic exocrine cells. Is that okay? Now, secretin primarily, its function is to increase bicarbonate production. Secretin is specific for bicarbonate. CCK is more specific for enzymes. That's the difference. Both of them will increase the pancreatic secretion, which is a solution mix of enzymes and bicarbonate. But secretin specifically increases bicarbonate. CCK specifically increases enzymes or bile secretion. Okay? So bicarbonate, as you understand, is what? A buffer that neutralizes what? Acid. So obviously, too much acid in the duodenum or low pH should be the stronger signal for S cells to secrete secretin. It makes sense. Because there's need for bicarbonate to neutralize that acid. Otherwise, gastric acid in the duodenum will cause ulcers if you don't neutralize it. Are we good with that? Okay, good. So far, so good. All right. So we understand these. Let's remove them. Okay. In the proximal duodenum, this area, in the first part of the duodenum, you have a lot of Brunner cells, which are mucus-producing cells. Brunner cells, okay? Brunner. Some will pronounce Brunner. If you want to call it Brunner, good for you. Okay. But nonetheless, they produce what? Bicarbonate. That means as the stomach acid is coming, Brunner cells will neutralize it first. And then if they reach to the second part of the duodenum, bicarbonate coming from the pancreas will neutralize it. Okay. You don't want acid in the duodenum to be, not neutralized because it will cause ulcers. You have to immediately neutralize it. The only organ in the GI tract that is resistant to strong acid is stomach. Every other organ is sensitive to acid. Same thing esophagus. So if esophagus will have ulcers, what do you think would happen with duodenum if there's too much acid? Duodenal ulcers. Okay. All right. So now we can go back to protein digestion. Okay. So when protein reaches the duodenum, right here, when protein reaches the duodenum, they need to be digested. They need to be digested, and they need to be converted to what? Peptides. Dipeptides, or tripeptides. That's our goal. At least we want to do that, okay? Now, I need to make this area bigger. So I don't need the S cells and I cells. I'm going to erase them to create myself some space. Just to create myself some space. And then gallbladder, I don't need it too. So as food reaches the duodenum, of course, S cells and I cells will be activated. And they're going to increase production of what? Pancreatic juice. Now, pancreatic juice will have what? I'll put TG for trypsinogen. Okay, CG for chymotrypsinogen. And then CP for carboxypeptidase, right? Okay, A for, or AM for amylase. Okay, and then LP for lipase. All these enzymes are produced. All of them are produced. They're mixed in the solution. They're all inactive, right? They're inactive. They're in the zymogen form. So to activate them, you have to have a mechanism. But now we have here brush border enzymes. In the duodenum, in the second part of duodenum, we have brush border enzymes. In these brush border enzymes, I'll use red for that, are attached to the surface, or let's just say green, attached to the surface of these brush borders, these green ones. These enzymes are known as enteropeptidase or enterokinase. They're not free enzyme. They're attached to the surface of what? Duodenal epithelium. They're attached to villi and microvilli. So enteropeptidase, the green dots, are enteropeptidase or enterokinase, same thing. Has two names. Enterokinase obviously requires what? ATP. What does entero mean? Intestine. Okay, so enterokinase are enzyme in the intestine that requires ATP. But they're brush border enzymes. Please write it down or remember, they are brush border enzymes. Enterokinase, enteropeptidase, they are brush border enzymes. Brush border enzymes. Are we good so far? Okay. Enterokinase or enteropeptidase. What does peptidase mean? Breaks down peptides or proteins, right? What does enteropeptidase mean? Breaks down intestinal peptides and proteins. Excellent. Now, what are enzymes made of? Proteins. So they break down intestinal enzymes, which are pancreatic enzyme in this case. Very good. So now, what do they activate? This is what they do. Enterokinase or enteropeptidase simply activates trypsin. So TG will be converted to what? To T. That's what it does. Okay. So TG, trypsinogen, will be converted to what? Trypsin. The most important enzyme of the pancreatic enzyme is trypsin. Okay, the most important enzyme of all pancreatic enzyme is trypsin. Okay. Now all the rest of them, these guys are, let me just do it on this side. These guys are activated to chymotrypsin, carboxypeptidase, amylase, and lipase with the help of who? Trypsin. So trypsin will activate all the rest of them. Okay. Maybe to keep it simple, let me just do it this way. So pancreas will produce these two enzymes, and then these guys are activated with the help of trypsin. Okay. So again, all I want right now for you to understand what happens in the duodenum. Duodenum is the most important site of digestion. Breakdown. It's the primary site of carb breakdown. Chemical digestion, yeah. It's the primary site of carb digestion, lipid digestion, and protein. Of course, protein stomach is more important, but this area as well. Okay. Yeah.
Sorry, what's CG and CP?
Chymotrypsinogen, carboxypeptidase, amylase, lipase. Okay. All right. So at the end of the day, simply food coming to the duodenum did two things. Number one, they activated I cells and S cells to release CCK and secretin. Secretin and CCK acts on the pancreatic acinar cells to increase pancreatic juice production. And of course, if the juice is squeezed and produced, it will go where? In the duodenum. In the duodenum, those enzymes are then activated by the help of who? Enterokinase and trypsin. Enterokinase and trypsin. And trypsin is the major activator, of course. So enterokinase will activate trypsin, and trypsin will activate all the other enzymes plus itself. You need to understand that trypsin can activate all pancreatic enzyme, including itself. So let me give you a sense of idea. You know, in acute pancreatitis, the trypsinogen is converted to trypsin by itself, and it activates all the pancreatic enzyme, and then the pancreas will eat itself. Because you have peptides, you have lipase, what are they going to do? They will break down everything that's in the pancreas, which is lipids, which is protein, which is carbs. So acute pancreatitis is emergency because of this issue, that the enzyme will start eating the pancreas itself.
Self-digestion.
Self-digestion. Very good. Okay, so far as I understand, we were successful in activating the pancreatic enzyme. Now these pancreatic enzymes, since we're talking about protein only now, okay, please, you understand the enzyme in the stomach, the enzyme of the pancreas, the cells of the pancreas, cells of the stomach. You're good with that, right? So now we can talk about protein digestion, carb digestion, and everything else. Okay. So let's talk about protein digestion. Protein digestion. So protein comes, let's say, stomach, and let's say duodenum. So what happens in this area? In stomach, protein. Now protein digestion in the oral cavity is minimum, not much. Not much happens in the oral cavity. Okay, so not much protein is digested. So protein in the stomach is converted to polypeptides. Very good. And small peptides. And small amount of amino acids, not a lot. Okay? And who does that in the stomach? Pepsin. Pepsin. And I'll put slash HCl. So that's the two things that helps protein breakdown in the stomach. Okay? In the stomach. So let's say this, let's say above here is the stomach. Okay? Above the line is the stomach. So in the stomach, what you do is you break down protein into peptide, polypeptide with the help of pepsin and HCl. Okay? And this will be carried into the duodenum. In the duodenum, these peptides are then converted to dipeptides. Okay? Maybe some tripeptides, some single amino acid as well. Okay? Now, who does that? So we have trypsin. Trypsin will convert it to dipeptides, tripeptides, okay? And how about chymotrypsin? Chymotrypsin, same thing. Chymotrypsin. Okay? Now these dipeptides are then converted to single amino acids with the help of carboxypeptidase. Which is actually exopeptidase. Trypsin and chymotrypsin are endopeptidase. Okay? So to amino acids. Also, you have some brush border dipeptidase. Brush border dipeptidase. Peptidase. What am I doing? Peptidase. Okay, so brush border dipeptidase, which will convert those dipeptides into what? Single amino acids. Okay? All right. Carboxypeptidase, trypsin, and chymotrypsin, they are pancreatic enzymes, whereas dipeptidase are brush border enzymes. Let me put it here, brush border. They are attached on the surface of duodenal cells and jejunal cells. Not proximal duodenum, distal duodenum, fourth part, mostly. Third and fourth part of duodenum. You will have dipeptidase, okay? All right, so you get single amino acids. Good enough. Now, single amino acids are then absorbed into blood, right? You remember that part? How are they absorbed? With the help of sodium. With the help of sodium. I'll cover that part for you, okay? All right, so there you go. Now, of course, release of trypsin, chymotrypsin, carboxypeptidase requires CCK. CCK. Yeah. Release of pepsin and HCl requires what? Gastrin, acetylcholine, or histamine. You know those parts. Let me write it down. I'll just add to that. So these guys require histamine. The secretion of these guys. Histamine, acetylcholine, or gastrin. And the release of trypsin, chymotrypsin requires CCK. Maybe some secretin. I'll put S. At the end of the day, what you did is you took... See, the problem is, we have only one problem, and that is protein and peptides are too large to be absorbed. The only thing you can absorb is single amino acids. So you have to break it down to single amino acid. Any problem in this process will lead to malabsorption, protein malabsorption. Yeah.
So the first up to for the blue line is in the stomach.
Mm-hmm.
And the peptide can cross over into the duodenum. And from this is all duodenum broken down to amino acids.
Mm-hmm. You will have some amino acid in the stomach, but not a lot.
Not as much.
Yeah. Okay. Okay, so that's protein digestion. Protein digestion. Okay, protein digestion. So if I were to do it, let's do it here. Just so you can see, you can picture this. Stomach, duodenum, and the distal part of duodenum, and let's say gap, and here is jejunum. Okay, so this part is jejunum. Let me see the green area. Whoa. The green area, let's say, is jejunum. Okay. Let's say the purple area is distal duodenum, and then you have the proximal duodenum. So protein digestion. Protein came here. It was converted to polypeptides with the help of pepsin and HCl. And you know who produced them. See, pepsin was produced by, I'll put C, chief cells. Okay, HCl by P cells or parietal cells. Good, done. And who activated parietal cells? Gastrin, histamine, and acetylcholine. Okay. Now, after a few hours or minutes, the peptide were dumped into the duodenum. When it reached to the duodenum, obviously, this food was coated with what? Acid. And then they activated. Whoa.
Brunner cells first.
Very good. So acid will activate Brunner cells, will produce bicarbonate, and then I cells. And I cells released what? CC. Wow, are you serious? CCK. In addition to that, they activated S cells, and they produce what? Secretin. So these guys will act on the pancreas, and when they act on pancreas, pancreatic juice is secreted, right? And the pancreatic juice included enzyme, which was trypsinogen. Let's just include trypsinogen for now only. Trypsinogen was activated with the help of enterokinase or enteropeptidase. So trypsin got activated. I'll just leave T. What T did, T was able to convert. I'm running out of room, so that's my issues. So now trypsin converted to, it activated chymotrypsin, carboxypeptidase, amylase, lipase, and all of them. But we're only concerned with trypsin, chymotrypsin, carboxypeptidase, and enteropeptidase. That's all. We're not concerned with lipase or amylase because they have to do with something else. Okay. So now trypsin, chymotrypsin, and trypsin were able to convert peptides into dipeptides. Polypeptides into what? Dipeptides and tripeptides. Okay. Now these guys were able to be converted to single amino acid by who? Carboxypeptidase. Carboxypeptidase. And then some of them were able to, and the other ones will keep going, right? Some dipeptides and tripeptides reach here. When they reach here, you have now brush border enzymes. And these brush border enzymes are known as dipeptidase. So they took these dipeptides and again converted them to what? Amino acids. So we succeeded so far. So we have succeeded in breakdown of proteins. Okay, you have to know these enzymes in these pathways. Now in jejunum, ileum, jejunum, especially in the proximal jejunum, you have enterocytes. I'll just draw one. Enterocytes, cells of the small intestine, enterocytes. Enterocytes have on the surface sodium, amino acid, co-transporter or symport. It transports amino acid and sodium. So let's say amino acid and sodium at the same time. So that's the absorption of amino acids. Okay, absorption of amino acid. But now, remember this channel, this symport channel, sodium, amino acid channel, is driven by sodium potassium ATPase, which is on the basolateral side, which continuously, let me just do it here, which continuously pumps what?
Sodium out.
Sodium. 3 sodium out. So automatically sodium will go in and it will carry amino acid with it. So look, amino acid transport into enterocyte depends on what? Sodium. It's sodium that drags amino acid with it. The charge on sodium is positive, and the charge on amino acid is negative. Obviously, they're going to attract each other. Okay? But the force is created by sodium. Potassium pump, which continuously pumps sodium out of the cell. Therefore, sodium is always inside the cell, is less. So automatically, sodium will keep going in from intestine into cells, always. And it will drag amino acid with it. Okay?
Sorry, Doctor, so why intracellular sodium is not as much?
Okay, so now I will do that. So let's just do this. Enterocytes. Where is, there you go. Enterocytes should have a luminal surface and yeah. Okay. So surface A, surface B, surface C, surface D. What surface A? Lateral. What surface C? Lateral. What surface B? Luminal. How do you know? Brush border. And what's D? Basolateral. Basal surface, okay? Now it's called basal. Why is the basal called basal? It's towards the blood or basement membrane. Very good. So let's include here blood vessel. In this case, the blood vessel will be superior mesenteric vein. Superior mesenteric vein. You already know that, you know, the entire midgut is supplied by who? Superior mesenteric vein and artery. I mean, you shouldn't be confused. So when you talk about any third, fourth part of duodenum, jejunum, ileum, ascending colon, transverse colon, it's all have to be what? Superior mesenteric vein. So by far the most important vein in terms of absorption is what? Superior mesenteric vein. Okay. So we were able to, again, there were brush border enzymes. Brush border enzyme known as dipeptidase. Dipeptidase were able to convert dipeptides into single amino acids. And that's what we want. Now, the channels that we have here, these channels, the channels that we have on the luminal surface. See, luminal surface will always have channels, not pumps. The luminal surface will always have channels, not pumps. So these channels can transport amino acid if sodium is available. If sodium is available. They cannot transport amino acid without sodium. So you can take all amino acid you want if you have no salt. You're just wasting it. So those of you who work out and you want to take supplements like amino acid and protein, accompanied by, I mean, they should have enough salt in there anyways, regardless. They should have it in the mixture of powder, whatever you call it. Okay, so amino acids are then brought in. Okay, now, there is a pump on the surface. This pump continuously pumps sodium, not directly into blood, to extracellular space, and then will diffuse. It continuously pumps sodium out. 3 sodium. So if you continuously keep pumping sodium out of the cell, would there be any time in your lifetime when sodium is high inside the cell? No. The only time if you have no energy. That's not life. That's death. As long as a human being is living or a cell is living, it is impossible for sodium to be high inside the cell. Otherwise the cell will die. See, remember we talked about cellular injury the first week. One of the signs for cellular injury was influx of sodium into a cell. Okay? And it is the sodium that maintains, that causes depolarization. Anyways, so there's a lot of problem with if you have too much sodium inside the cell. Roughly speaking, intracellular sodium is 14 milli equivalent. Compared to outside, it's 140. I like the 44. Here you go. Although it's 42 exactly. More force. Okay? So huge difference. So that means if you open this gate, obviously sodium will go in, because inside is very little compared to outside. Okay, there's more pressure, there's more concentration outside of the cell compared to inside, so automatically, and it will drag amino acid with it. And this is maintained by who? Sodium potassium pump. Because this pump does not stop. The only day it will stop is when there is no ATP available. So as long as there is ATP, you'll keep pumping sodium out. Always, continuously, non-stop. Non-stop. And that's why we have to keep eating sodium, because some sodium is excreted in urine. You lose it, and you lose it in different functionality, right? So our life does depend on sodium. So I hope you understand. Now, this is how amino acid, and then these amino acids will diffuse into the superior mesenteric vein, and from superior mesenteric vein, these amino acids are carried where? Liver, which is the most important organ when it comes to protein metabolism, of course. Of course. Don't forget, aminotransferase there, right? The majority of aminotransferases are found where? In the liver. Okay? Alright, so again, let's hope you understood. Protein digestion, it begins in the oral cavity, but there's not much happening. And then protein reaches the stomach. In the stomach, proteins are converted to polypeptides or peptides, some amino acid, with the help of pepsin and HCl. But of course, you know what happens to HCl and pepsin. They're produced by gastric cells. And gastrin will activate parietal cells and chief cells. Okay? Now, once you have peptides and polypeptides, they'll be washed away, pushed. This food will go into the duodenum. When it reaches the duodenum, the same food content will activate I cells and S cells. I cells and S cells, in relation to that, will activate pancreatic cells to increase pancreatic juice secretion. When you have pancreatic juice, some of those enzymes are peptidase. And in terms of protein, peptidase will be more secreted. So the peptidase will start protein digestion in the duodenum. In the duodenum, they will start protein digestion. And you will have dipeptides. And essentially, the dipeptides are then converted to single amino acid with the help of dipeptidase and carboxypeptidase. And we're done. And then you have to absorb them with the help of sodium. Okay, let's go with carbohydrate metabolism. Now, carbohydrate, let's say oral cavity, and then we have stomach, and then we have duodenum. Okay. About 15% of carbs are digested and absorbed in the oral cavity. Now, in oral cavity, sweet things can be absorbed and digested more than anything else, than protein, or sugars in general. In stomach, minimum. I'll just bypass this. Not much. Not much carb digestion occurs in the stomach. So I will remove the stomach just to create myself some space. Okay, so that means duodenum is the major site of carb digestion. So these carbs, when they reach duodenum, carbs is the same thing as polysaccharide. Good. So we'll have some monosaccharide, trisaccharide, polysaccharide, mostly polysaccharide. In the duodenum, these guys are then converted to disaccharide, trisaccharide. Okay. Now, of course, in the duodenum, the thing that helps break down of these carbs into disaccharide and trisaccharide, especially mostly disaccharide, is pancreatic or P amylase. Very good.
You also have amylase in the oral.
Yeah. So pancreatic amylase. Now the 50% of carbs that are digested here with the help of salivary amylase or oral amylase, which is different than pancreatic amylase. So now you'll get disaccharide. Carb is much easier. What are some disaccharides? Let's write down their names. Lactose, sucrose, and maltose. Okay? Now, the only thing we can absorb again is what? Monosaccharides. The only thing we can absorb is monosaccharides. Okay? So now, these disaccharides have to be converted to monosaccharides. So lactose will give you glucose and galactose. And maltose will give you glucose and glucose. And sucrose will give you? Very good. So let's say from 3 molecules of these disaccharides, you'll get 1 fructose, 1 galactose. And how many glucose? 4. 2 from maltose, 1 from lactose, 1 from sucrose. Okay? So the ratio of glucose is always higher in your diet, right? Okay. And again, you have to drink milk to have galactose. Okay, now these guys, this conversion is done by brush border enzyme. Again, the name of those enzymes will be sucrase, lactase, maltase. And then similarly to amino acid, these glucose are then absorbed into what? Enterocytes with the help of sodium monosaccharide transporter, or known as GLUT. GLUT what? GLUT 1 and 5. GLUT 1 and 5. GLUT 1 and 5. Good job. Now let me do it in another way. So, there was some digestion that occurred in the oral cavity, 15%, with the help of oral amylase, right? Nothing in the nothing in the esophagus, nothing in the stomach, and then let's move on to the duodenum. We'll make duodenum bigger. Okay, so here we were able to convert these polysaccharides into disaccharides. And you know what? You know the name of disaccharides, so I'll use them. So, lactose, sucrose, and maltose. Okay? With the help of who? Pancreatic amylase. Which means, again, you need what for this? I cells to release what? CCK. S cells to release what? Secretin. Okay? So this will happen the same thing. Remember, pancreatic juice is not just made of one type of enzyme. That means at this time you might also have some lipase swimming around. You will also have peptides swimming around. So it depends what food you eat mostly. You know, if you eat mostly lipid food, I cells are activated more. Okay? So it depends. It depends what you're eating. And I'll come to lipids. At the end of the day, all pancreatic juice will have lipase, amylase, and peptidase, and nuclease. All of them. So, and they will do appropriate things. I have to break it down one by one so it makes more sense. Now, then we have brush border enzymes. In this case, the brush border enzymes are sucrase, let's say S, maltase, M, lactase, L. Okay? So maltase, no good. Let's say maltase, M maltase. Now this will take maltose and convert it to what? Glucose and glucose. Okay? And then these guys are then absorbed with the help of GLUT 1. Okay? Yeah. So GLUT1, and they will go into cells. Good?
Sodium to go.
Yeah. Let me make the enterocyte bigger. Just say glucose. Enterocyte. So we should have GLUT1. And we should have GLUT5. And the basal surface you should have GLUT2. GLUT1. GLUT2. And GLUT5. There you go. Okay, so sucrose is then converted by who? With the help of sucrase. It's converted to glucose and fructose. Okay, and lactose is with the help of who? Lactase, right? And it's converted to glucose and galactose. Now, galactose and glucose are absorbed with the help of GLUT1. Galactose and glucose are absorbed with the help of GLUT1 plus sodium. Okay, and then GLUT5 takes fructose plus sodium. Okay, and all three of them are then taken to the other side by who? GLUT2.
So GLUT1 and sodium transporters. What about
Yeah.
GLUT2?
Yeah, also sodium dependent, but yeah, there's not much sodium dependence as much as GLUT1, but it can be sodium bicarbonate, many things.
So it's an antiport? Or
No, it's simport.
it's still some.
Is it variation between GLUT1 and GLUT5 because the fructose is different shape?
Yeah, exactly. Okay, so now we're done. So what we did is we took all this monosaccharide into blood, superior mesenteric vein, and then you can do the rest, what we talked about before. We'll come to that. Okay. Okay. Let's go to lipids. Lipids. We still have 10 minutes? That's good. Okay, lipids. For lipids, we need gallbladder and liver. Okay? So we need gallbladder and liver. And then we also need pancreas. Lipid digestion starts in the duodenum. Minimum digestion in the oral cavity and stomach. Minimum. So let's say these lipids. Now, essentially, when we eat lipids, it will be a lipid goblet, a huge lipid goblet. Okay, so it's many lipid particles there are put together as a goblet. Okay, so that's what you will see: different lipids particles all glued together. Okay, when this reaches duodenum, so of course some fatty acid might be loosened and so forth. They'll activate eye cells. Number one, lipids primarily act on eye cells. So when they activate eye cells will release what? CCK. And CCK will cause contraction of what? Gallbladder. That means a lot of bile will be released into where? Into the duodenum. Okay? A lot of bile. So what does bile do? Bile will start breakdown of the fat goblet. And the term for that is what? Emulsification. Very good. So step one in lipid metabolism is CCK. And CCK will cause contraction of gallbladder. So gallbladder contraction or motility. And then step two, this will lead to bile secretion. Not only is there bile secretion, but there is also bile synthesis. So CCK acts on gallbladder to increase bile secretion. but it acts on the liver to increase bile synthesis. So we need to understand bile is made, bile acids, not just bile. Bile acids are made where? In the liver. Liver makes bile acid. Gallbladder stores it. Liver makes bile acid. Gallbladder stores it. So CCK acts on both, primarily acts on the gallbladder to release the stored bile acids. And it also activates what? The liver to make more bile salts and bile acids. Good? So that's one thing. At the same time, of course, S cell will be also activated to increase secretin, and that will increase bicarbonate. So now, what we did is the CCK acts primarily on gallbladder and liver. And they will also act on the pancreas. And pancreas will release what? Lipase. Lipase. So we have both bile and lipase being secreted at the same time. So, but first, let's do this. First, when this fat goblet comes, bile salts or bile acid, same thing, okay, will convert this lipid goblet, and it will crumble it to small pieces, individual pieces here, there, and there. Okay, so it will crumble. It's almost like cutting a pizza into different pies. That's what it does. Now, bile salts, bile acids are like soap. It breaks down and makes lipids soluble. Okay, so that was emulsification. Emulsification of lipids, so I should put here 3. Lipid emulsification is done with the help of bile salts, bile acids. So you need gallbladder and liver for lipid digestion.
So it just makes the lipids, the cholesterol, soft.
No, it's just, you know, like if you have, let me see. What kind of donuts when you touch them, they crumble? Just imagine it. Doesn't matter what. Who cares about the name? Imagine you take some donuts and some round sweet and you touch it, you hold it, they crumble. So you have to always be careful with that. And that's what bile salts will do to this lipid goblet. Now, the thing is, you can also, at the same time, you have lipase, right? See, lipase is already here. But the thing is, lipase cannot have access to the inside of the goblet. It cannot just penetrate the goblet and start breaking it. So for lipase to do something, the bonds must be exposed. The bonds between different lipids must be exposed. Okay? So now we will talk about, we have phospho, different lipases, right? So let's say phospholipase. Okay? You have cholesterol esterase. Okay? And then you have general lipase, which will take care of what? The triglyceride. So the food particles that we should have here is triglyceride. Let me use a different color. The type of lipid we should have is triglyceride, cholesterol esters, and what's the other one? Cholesterol esters and the phospholipids. There you go. Phospholipids. Okay?
Isn't that term called a Kylie right now?
No. We'll come to that. We'll come to that. It's in the process. Yeah, we haven't got there yet. Good job, good job. So triglyceride are converted with the help of lipase. They're converted into fatty acid. What is the triglyceride made of? Fatty acid and what? Glycerol. How many fatty acid? 3. 3 fatty acid and 1 glycerol. Okay. So now phospholipid will be converted to with the help of phospholipase, right? I'll just ignore these too many arrows. Just add it to this. Phospholipase will be converted to what? What is phospholipid made of? 2 fatty acids, 1 phosphate, and glycerol. So I'll add 1 more glycerol. That's 2 so far. Okay. What is cholesterol esters made of? Cholesterol, of course. And the ester part is what? Fatty acid. So at the end of the day, what are you getting? You're getting glycerol, cholesterol, fatty acid, and phosphate. Done. Now this is what phospholipase, cholesterol esterase, and lipase would be able to do. Lipase primarily will act on triglyceride, or you can call it triglycerase, or triglyceridease, doesn't matter. Phospholipase will break down phospholipid cholesterol ester will break down the bond between cholesterol and fatty acid. See, fatty acid attached to cholesterol is known as cholesterol ester. Okay, so we have done this so far now. Good.
So cholesterol is basically cholesterol and fatty acid.
So far we have, these are the products of this lipid digestion. And let me get rid of these guys. So I'll just to save some room, I'll make this, there is the lipases. See, lipases will break down individual molecule, whereas bile salt will just crumble, cut into small pieces, so lipase can act on it. So the end product of lipase will be fatty acid, correct? Will be glycerol, and will be cholesterol, and will be phosphate. That's all. Phosphate is electrolyte, so it'll be absorbed in the duodenum. Done. No big deal. So let's ignore phosphate, which is not our concern. Now we're concerned with cholesterol and fatty acid. And what happens to glycerol? Glycerol is also absorbed. So, okay. So we have these small lipids, now we can absorb them, okay? To do that, we have to go back to enterocytes. We have to go back and do the same enterocytes. Remember, these enterocytes were able to absorb amino acid and glucose, monosaccharide and glucose, okay? Now, we have these phospholipids. Okay, so phospholipid looks like this, right? Okay, fatty acid will look something similar. Now, the question is, now the fatty acid are actually, so we had fatty acid, we had glycerol, and we had cholesterol, right? Okay. So the cholesterol will be in the center, like this. Sorry. Cholesterol can be absorbed directly because they're permeable to membrane. You remember that when we talked about first day of class? What are some things that can cross the membrane freely? Cholesterol is one of them. So it will go easily. Glycerol will be absorbed through the GLUT transporters. Okay, so that's not a problem. Fatty acids are charged, so they're not easy to absorb. So what happens to fatty acid? They form these things called micelle. Okay, micelle. Now, if you think of fatty acid, remember they have this is the shape of fatty acid. So it has one end that is hydrophobic, the green end, and it has the yellow end which is charged hydrophilic, water soluble. We discussed this earlier, remember, a month ago. So now all these fatty acids, so let's just say the green part is the tail. So all the tails will start facing each other. They'll organize themselves into this spontaneously. In the yellow part, let's just make it red so I can see it good. The red parts will be facing the outside. Now this is soluble in what? In water.
So my cells are.
Yeah. Okay, so just for, it will crumble. You know, like if you put lipid in water, automatically it will organize themselves into a bubble or a blob or a glob or whatever. So now the micelle is absorbed. Okay, it's absorbed through the cell wall or the cell membrane. Now, so far when it comes here, we have within the cells we should have a nucleus, and we should have ribosomes, which this is rough endoplasmic reticulum. And then let's say here we have smooth endoplasmic reticulum, not attached to the nucleus. Yellow should be the smooth endoplasmic reticulum. Green should be rough endoplasmic reticulum. This is where enterocytes. We're not talking about hepatocytes. We're talking about enterocytes, cells of the jejunum. Okay, cells of jejunum and distal duodenum. So what we did is we were able to bring fatty acids here. We're able to bring fatty acids. We were able to absorb fatty acid, glycerol, and cholesterol. All these things are brought into the enterocytes. Good? Okay. Smooth endoplasmic reticulum will convert cholesterol back to cholesterol esters. Smooth endoplasmic reticulum, what does it do? It's site of lipid synthesis, true? Okay. So the problem is we cannot absorb them, so we have to break them down to make them smaller so that we can remove them from intestine into cells, right? So we had to do that. Now, the smooth endoplasmic reticulum, what it does, it will recombine them. And it will give you triglyceride one more time. It will give you phospholipids. And it will give you what? Cholesterol esters and cholesterol. You had to break them before so you can transport them. It's almost like, you know, when you want to take your bed or TV, whatever, you know, you're moving, you have to deassemble it, right? So you can fit it, and then when you go back to your new home, you put it back together. Same thing. So smooth endoplasmic reticulum will reorganize these lipids back into the same shape. Now, the rough endoplasmic reticulum will produce proteins. Of course, we know the rough endoplasmic reticulum only does one thing, protein synthesis. And these proteins are known as apoproteins. In this case, one is beta 48. And the other protein is C or C2. Okay, so again, there's a lot of apoproteins. We talked about it. Do you remember those? Beta 100, beta 48, A1, A2, C2, right? And E. One more, it should be produced here. That's E. Okay? So these are the protein. These are known as apoprotein. Apoprotein. They're produced where? In the enterocytes. Not all of them. These three. These three. The other proteins are produced in the liver. Okay. Very good. I can see lipid digestion is a little bit more informative than others, so don't hate it. It's okay. Now, triglyceride are the most let me just put this. Triglyceride, let's call them red. That's triglyceride. And let's call green phospholipid. And let's call blue cholesterol. Good? Now, triglycerides are the most lipids, so now it's time to make chylomicrons. So the enterocytes will combine. See, chylomicron is a combination of proteins and lipids. It's a combination of protein and lipids. Whereas myceli is only lipids, only fatty acid. Only fatty acid. Maybe some cholesterol trapped within it. So, the chylomicron, now it's time for chylomicron. So, again, all of this is made where? In the enterocytes. So I'm going to erase these things. So think of the whole page being enterocytes. So triglyceride are mostly the storage form of lipid. They're the least soluble in water, right? They're the least soluble in water, so the core of chylomicron will be made of what? Triglyceride. And then you have cholesterol, which is blue, will be the next layer. And then the form of lipid that's actually soluble in water is what? Fatty acid or phospholipid, right? Fatty acid is phospholipid. Very good. So these phospholipid will cover the outside layer, which is in contact with water. Don't think of this as a 2D structure. This is a round. This is a ball of cells or fat. This is a globule, the round spherical. Chylomicron is a spherical molecule. So the outer coating of the sphere is by phospholipid. The inner core is triglyceride. Between the triglyceride and phospholipid, what do you have? Cholesterol. Okay. Now, in addition to that, you need receptors. You need a receptor. So here you will have protein E. Protein E allows these chylomicron to be absorbed from enterocytes into what? Lymph. Excellent. Lymph. Okay, and then you have protein C also attached to this. Now protein C, I mean, if you don't like these numbers, let me do it this way. Protein C, there you go. This is protein C. Okay, so protein C is purple. C. What other color can I use? Let's say light blue. And then so this, let's call it protein B48. And then we have E. Let's make it orange or yellow. Oh my god, why did I keep... There you go. That's E. Now, does it mean there's only one? No, it could be multiple proteins, so I don't have room. So here you go, there's one more, there's one more. And let's say pink, one more. And let's say blue, here and here. Uh-oh, not good blue. There you go. There you go, okay? So at the end of the day, what's this chylomicron? It's a combination of protein and lipids, but you have to know the organization of lipids. They're organized in layers. The core is triglyceride, coated with cholesterol, and then the outer coat, phospholipid. And then, of course, sticking out from all of this would be protein. Protein has to be sticking out because they're receptors. Okay. Now, as far as, C was to activate phospholipase C. Okay, so this protein C is a lipase activator. Lipase activator. So when this chylomicron reaches the blood, you have to break it down back to what? With the help of lipase or protein C, it is broken down back into what? Phospholipid, triglyceride, and cholesterol, and then you can do whatever you want with them appropriately. We've discussed this before. I'll come back to them. So that's protein C. Now E was to help it absorb from enterocytes into what? Lymph. So absorption. 48 is to carry it in blood into liver and so forth. Okay, so E and B, they both help in absorption. Now each enterocyte, okay, each enterocytes will have, if not enterocytes, so maybe you should see this picture in your book. Each villi or microvilli, let's say this is a villi and they will have microvilli, will have a central lacteal. This is central, yellow is not good, let's see. In the center of it you will have this lymphatic vessel. Next to it you will have, so let's say the branches of superior mesenteric, let's say superior mesenteric will come and then it will carry blood to this area, and then you will have a vein also removing the blood from this. So everything else, for example, when we talk about glucose and amino acid, they will absorb into what? Vein. Amino acid were absorbed into superior mesenteric vein. Glucose or monosaccharides. I'll just put monosaccharides. Monosaccharides were absorbed into vein. But lipids were absorbed directly into the lymphatic. In this case, chylomicron, of course. See, veins, superior mesenteric vein will become portal vein, right? And that means portal vein only drains into what? Liver. So all food being absorbed through venous circulation would have to go through liver. Liver is a chemical factory. We want to make sure everything is okay. We want to make sure there's no toxin in there. We want to make sure there's no problems in there. It will clarify and detoxify your food before it goes into your blood or your heart or your brain or anywhere else. But lymph bypasses the liver. It goes directly into jugular vein and brachial vein junction. Okay? Alright, so there you go. You should know. We're done, so make sure you know